Hey, hello. Welcome to our YouTube space. Today, I want to focus on chemistry, and we want to focus on a very interesting topic and also a very common topic. And the topic is called the mole concept. So, the mole concept is basically a Form 3 topic, and it is topic 2, and that is what we want to do. So, this topic is very important, and that's why we want to do it today. Okay, so this is a very common topic in exams, and especially in chemistry practical, it will always be there because there's a certain question called the titration. So from the titration, you're normally able to see this question, or even sometimes in chemistry paper 1 and also in chemistry paper 2. In a nutshell, the mole concept is really important. So some of the things that we learn in the mole concept will be, as you can see from my table of contents, so we learn about, so these are some of the things that we learn about. We learn about something called relative mass and the Avogadro's constant. Number 2 here is the empirical and molecular formula. We'll also study about the molar solutions. Number 4, we'll capture about stoichiometry of chemical equations. We'll also talk about the volumetric analysis, which is the titration. We'll talk about atomicity and molar gas volume. So these are the things that we'll talk about. Okay, so let's move and dive into it. So the mole, beautiful indeed, beautiful. I'm so psyched to do this topic. Chemistry is life. Chemistry is very interesting to do chemistry. Okay, so the mole. So the mole is the SI unit for amount of substance. Okay, this is how it goes. I believe you have ever been to a cereal shop, and when you went to the cereal shop, there's no single day you have asked the shopkeeper to give you a single grain of rice. Neither have you asked the shopkeeper to give you, maybe if you go to now maybe a kiosk or a different shop, you have never asked them to give you a single crystal of sugar or even of salt. Okay, there's no single day you have gone to the shop and maybe again to the cereal shop and maybe asked for a single grain of beans. Okay, so what does that mean? So in scenarios that the substances are very small, normally what do you need to do? You must buy the commodities in bulk. So for example, the rice. Okay, there's no way you can buy a single grain of rice. Rather, the rice is going to be packed either in a quarter kg, a half kg, 3/4 kg, 1 kg, 2 kgs, 3 kgs. So when the commodities are in small particles, they are put in a group. You put them in a group, then that is how you sell them. The same with also moles. Okay, so also the atoms, the atoms, they are also very small. The electrons are very small. The molecules are very small. The ions are very small. Okay, so you cannot consider a single atom, a single molecule, because they're very small, just like the rice. A single grain of rice, no, you need a collection of many of them. So the same as now the chemistry, the particles, now the particles, the molecules, the atoms. So these chemistry related substances, so they are very small. So you need a collection of them so that you can measure them. So the same way we use kilogram to measure rice, to measure beans, to measure sugar, to measure salt. It's the same way in chemistry, molecules, ions, atoms. We now use mole. because they're very small. So we put them in a group and it will give us the mole. Okay, yes. So for example, let's say maybe this is not an estimate. Okay, so maybe 1 kg of rice, for instance, maybe 1 kilogram of rice, maybe 1 kilogram of rice. If you count those grains, maybe sometime you can have maybe 2,000 of those grains. So maybe 2,000 grains of rice gives us 1 kilogram. Okay, but now in moles there's a certain constant. Okay, and this constant, there is the person behind it. He's called Avogadro. So in chemistry, Avogadro was able to tell us that 6.023 multiplied by 10 raised to 23. So this one is the Avogadro's constant. So in moles, for let me get to the rice concept. So maybe 1 kilogram, you need maybe 2,000 grains of rice. So in moles, you need 6.023 multiplied by 10 raised to 23 particles or molecules or atoms to make a single mole. So this one is equivalent to 1 mole. So if you can count 6.023 times 10 raised to 23 atoms, then you have 1 mole of something. Okay, yes. So just like maybe if you can count 2,000 grains of rice, you can get 1 kilogram. Also the same, if you can count 6.023 times 10 raised to 23 particles or molecules or ions or atoms, then you also have a single mole. So that is now the mole. Okay, so under the mole, we normally have the relative atomic mass and you have the Avogadro's constant. So what is really important at this point is the Avogadro's constant. So the number of atoms, okay, the number of atoms in one relative atomic mass unit of any element is basically now this. So what is very important here is the Avogadro's constant. So the Avogadro's constant is 6.023 times 10 raised to 23. Okay, and this one is now the Avogadro's constant. Avogadro's constant it is represented by letter L. Okay, it is represented by letter L. So the Avogadro's constant in exam you'll always be given in bracket. It will always be written there. Okay, so a mole is the amount of any substance that contains Avogadro's number of particles, whatever I've just explained. Okay, and it can be these things, whatever I was telling you. So it can be 6.023 times 10 raised to 23. It can be atoms, it can be molecules, it can be ions, it can be electrons. Okay, yes. Then there is another thing that is now very, very important. There's another thing here that is very, very important that you need to learn about. This one here. The mass in grams of 1 mole of a substance is referred to as the molar mass. So you need to know about something called the molar mass. What is molar mass? Molar mass, it is the mass of 1 mole of a substance. The mass of 1 mole of a substance is called molar mass. Okay, for example, let's talk about sodium. So let's try and understand what is 1 mole of sodium. So a single 1 mole of sodium, it means that we are going to have 6.023 times 10 raised to 23 atoms of sodium. So if you can have 6.023 times 10 raised to 23 atoms of sodium, then you have 1 mole of sodium. After having this 1 mole of sodium, if you can take a beam balance and measure the mass of sodium which has 6.023 times 10 raised to 23 atoms, because that is what will give us 1 mole, because a mole is a substance which contains 1 mole of a substance, that is 1 mole of a substance contains 6.023 times 10 raised to 23 atoms, particles, ions, electrons. So if we have a sodium atom which has 6.023 times 10 raised to 23 atoms, then it is considered to be 1 mole. So if you weigh that 1 mole of sodium, the weight that you get is the molar mass. So what does that mean? The molar mass will always be the mass of 1 mole of a substance, and the mass of 1 mole of sodium is always 23. So they are always specific, okay? Yes, so most of them are common. For example, 1 mole of hydrogen normally weighs 1 gram, okay? Yes, oxygen, 1 mole of oxygen weighs 16 grams. 1 mole of carbon has a molar mass of 12. 1 mole of nitrogen has a molar mass of 14. So those are the grams, the molar masses. 1 mole of sulfur has a molar mass of 32. 1 mole of sodium, 1 mole of sodium has a molar mass of 23. Okay, so some of them are very common and you'll be using them as we proceed. Okay, yes, 1 mole of calcium has a molar mass of 40. Okay, 1 mole of iron is written as Fe, as a molar mass of 56. So there are plenty of them and we'll continue to use them. So those are the molar mass. They're normally given in equation. Okay, they're normally given in equation. Now let's proceed to the formula. Yes, so now you need to know this formula. So the formula is here. It is also in form of a table. The formula is here. It is in form of a table. So you need this triangle. So the upper part is mass in grams. So where we have mass in grams. So mass in grams. Then the lower side of it, we have the molar mass and the number of moles. So if we want the number of moles, you just try to, okay, so if you want the number of moles, so then you try to block the number of moles. So what will be left will be mass in grams over molar mass. That's why the formula is mass in grams over molar mass. Mass in grams over molar mass. Mass in grams over molar mass. So let's say maybe we want molar mass now. So these are the formulas that you need to master. Molar mass. So what if we want the molar mass? So if you want the molar mass now, you try and block the molar mass. So if you block the molar mass, so you'll be left with mass in grams over number of moles. Mass in grams. Mass in grams over number of moles. Over number of moles. And what if maybe we want mass in grams now? What if we want now mass in grams? Maybe what if we want mass in grams? So if we want mass in grams, so mass in grams, it will be multiplication, because now if you try to block mass in grams, if you try and block mass in grams, so you look at what is on the lower side. Okay, so if you try and block mass in grams, now you look at what is left there on the lower side. They're by side, because they're now going to be side by side. So when it is side by side, this side and this other side, you multiply. So side by side you multiply. So you multiply. Okay, yes, so that will be molar mass multiplied by, so that is the formula, molar mass times moles. So that is these are the 3 formulas that you need to master. I believe you're moving on nicely. Okay, let's proceed. So those are the formulas. So let's look at a very simple example. Let's look at a very simple example. So here is the thing. Calculate the mass. So this one is basically the mass in grams. In chemistry, the masses should be the most common unit that these masses will be expressed, especially in moles. They'll always be in grams. Okay, yes. Calculate the mass of 0.4 moles. So we have the moles. So in this scenario, we have the moles. We already have the moles of calcium. So we want to calculate the mass in grams of 0.4 moles of calcium. So we have the moles. Then in bracket, what is normally given in this bracket are the molar masses. The molar masses. So we have moles and we have the molar mass. So what do you want? Mass in grams. So according to the formulas that we had written before, so we understand that mass is equivalent to molar mass times number of moles. And what is our molar mass? It is what is given in the bracket. The molar mass here is 40. So the molar mass is 40 and the moles we were given to be 0.2. 0.4, sorry, 0.4. So you multiply the two. So 0.4, which is moles, multiplied by 40, which is the molar mass, you get the answer to be 16 grams. So that is our first simple example. Let's go to example number 2. Determine the number of moles. So in this, the keyword here is to find the number of moles. So the other one, we are finding the mass. So in this one, you're finding moles. So you have been given the mass in grams, which is 13.5, and you have been given also aluminium as a molar mass of 27. What is given in the bracket are always the molar masses. So you need to know the formula that, because in this one you want the moles, but remember moles is equals to mass in grams over molar mass. So you just substitute. So mass in grams is 13.5. Then you divide with 27 because you want the number of moles. So if you do so, if you divide the two, you get 0.5 moles. You get 0.5 moles. Yes, you see how simple it is. Very easy, very easy. So in moles, we'll be using two ways to approach the equations. So there's something called the mole concept, the formula. You can be using the formula or the concepts. So I'll be showing you this thing using the formula and also the concept as we move. Yes, but it is very simple to understand moles. Let's proceed. I believe up to that point we are very okay. We are very okay. Yes, let's go to something called empirical and molecular formula. Let's go to something called empirical and molecular formula. Okay, empirical and molecular formula. So the first thing is to know what is empirical formula. In exam, they normally ask what is empirical formula. Okay, so in exam, they normally ask what is empirical formula. And the definition, I've just circled it in the blue using the blue ink. So what is empirical formula? So before I read out the definition, first let me show you something here. I want you to have an idea about the empirical formula. Okay, there is something called magnesium oxide. We want to write the chemical formula for that, magnesium oxide. So magnesium is in group 2, therefore it has a valency of 2. So I'm talking about magnesium oxide, and oxygen itself also has a valency of 2. So the valencies here are the same. So already we can consider they have been swapped, because normally you swap the valencies, but if they are the same, even if you swap them, they are still going to retain the same valency. So magnesium has a valency of 2 because it is in group 2, and oxygen has a valency of 2 because it is in group 6, so it gains 2 more electrons. Now you don't leave it at that point, so you divide both sides by 2, then you're going to get 1, then you ignore the 1, then finally you now have your MgO. So now the MgO is what we consider to be magnesium oxide. So what have we just done? We have simplified it. Okay, let's look at another scenario. Carbon 4 oxide. Carbon 4 oxide. Okay, carbon 4 oxide. So carbon 4 oxide, carbon which has an oxidation number of 4, and the oxidation number works just like the valency. So that's why I've written C4, and oxygen as usual has a valency of 2. Then you swap them. The C now takes the 2, and the oxygen now takes the 4. Then you simplify them, because 2 and 4, okay, 2 and 4, we can still simplify them by dividing both sides by 2. So divide by 2, divide by 2. So if you do that one, we get now C. Our C will be 1 and our O will be 2. Then we basically ignore the 1, so we are left with CO2. So we are left with CO2. So we have simplified it. So what are these things? These are now the empirical formula. Why am I calling them empirical formula? I'm calling them empirical formula because I've simplified their formula. I've not left their formula the way it was at the beginning, because I've simplified them. So when you simplify this chemical formula, whatever you remain with is called the empirical formula. Okay? Yes. And they have whole numbers. You don't divide in a manner that you now have decimals. No. You should always have whole numbers. So that is what an empirical formula is. So in writing, because in exam, sometimes you might be asked what is empirical formula. So the empirical formula of a compound, what does it do? It shows the simplest whole number ratio. It shows the simplest whole number ratio in which atoms combine to form the compound. The way you can easily see it in the few examples I've given there below. Let's now, we want to see an example of empirical formula. I want to give you a certain example here. Let me get to it. Yes, we can do this example. This example 2. Okay, we can do this example 2 here. So let's do this example. So how do you calculate? How do you basically calculate empirical formula in exam? So this is how you go about it. So here's our first example. The percentage composition by mass of an oxide of iron is 70% iron, so iron is 70%, and 30% oxygen, Determine its empirical formula. Then in bracket, you've been given the molar masses. Fe is the symbol for iron. So iron has a molar mass of 56 and oxygen has a molar mass of 16. So how do you normally do it in exam? So in exam, we normally do it in form of a table. So where you need the element, let me try to squeeze it this other side so that I have some good space. Element, normally do it in form of a table. Then you put your elements. In this scenario there were 2. So the first one was iron, which is Fe. You know, iron in Latin it is called ferrum. And that's why it has the symbol Fe. Then oxygen is that. Yes, so the element, so those are the elements. Then you want the percentage composition. Should write that in good. Percentage composition. So percentage composition, iron was 70 and oxygen was 30. Okay. Then we now go to we need their molar masses. Okay. We need the molar mass. So the molar mass of iron is 56, and the molar mass of oxygen is 16. Then we now find the moles. For that, we now find the moles. So moles, remember moles from the equation, from the formula at the beginning, I told you that moles is equals to mass in grams over molar mass. Moles is mass in grams over molar mass. So here, we don't have the mass in grams, but you have the percentages. Because you have 70% and you have 30%. Okay, let's say maybe if this thing was to be 100 grams, so out of 100 grams, and the percentages are 70 and 30. So if it was to be, if this oxide of iron was to be of 100 grams, then what is 70% of 100 grams? It would be 70 grams. And what is 30% of 100 grams? It would be 30 grams. So these percentages act also as the masses, because if this thing was to be in 100 grams, the masses would be 70 and 30. So in this equation of empirical formula, you normally use the percentages as masses. So the number of moles, remember, number of moles is mass over the molar mass. So our mass are the percentages. So you take 70, you divide by 56. You take 30, divide by 16. So you get certain answers. So the answer that you get in this one is 1.25. The answer that you get in the other one is 1.875. Okay, yes, then you are not done yet. So you are still proceeding with our table. So after doing that, then you now go to the mole ratio. So in mole ratio, you write the answers for the moles. So the answers were 1.25. Then the other one was 1.875. Then after finding that, you now divide both sides by the smallest answer, the smallest number. So you look at the numbers that you have, then you pick the smallest one. Of course, 1.25 is smaller than 1.875 because 1.2, 1.8. So this one is a smaller one. So divide both sides by the one that is smaller than the other. So which in this scenario is 1.25. You also divide this other side by 1.25. So here you get 1, and this one if you divide you get 1.5. So these are our mole ratios. But remember one thing. Remember that we said that the mole ratios, should be in whole number. The definition of empirical formula that we had given was the number, the whole number ratio. Okay, the whole number ratio of atoms when they combine to form the compound. So it means that the empirical formula should be in whole numbers, not decimal. Okay, yes, so we must make this thing to be in whole numbers. Okay, yes, so we have 1 and we have 1.5. 1.5 you cannot round off. That is will lead us to a very big error. Okay, yes, something that you can round off is something that is either to 0.0, 0.1, or even 0.9. So those are some of the things that you can round off. Something like maybe you have 0.9, maybe you have something like 0.0, you have something like 0.1. These are the things that you can round off. But these are the ones you must multiply it by a factor. For example, if you had 3.9, you can round off to 4. That one is okay, you can round off that one. When you have something maybe like even 5.0, you can just leave it as 5. Then if you have maybe something like, maybe you have 8.1, you can round off on that 8. So these are some of the things that you can round off, 0.9, 0.0, or 0.1. If you get an answer that is 0.9.0.1, you just have to multiply by a certain factor to get the whole numbers. So in this scenario, that is what exactly you're going to do, because 0.5 you don't round off, so we multiply by something. So you start at 2 as you move till you'll be able to get whole numbers. You multiply by 2, you see if you can get the whole number. You multiply by the same thing on both sides. You multiply 3 on both sides, you see if you're able to get the whole numbers. You multiply by 4 on both sides, you see if you can get the whole numbers. You multiply by 5. Before you reach 10, you'll be able to get 2 whole numbers. So let's start with 2. So if I multiply 2 on this side, 2 times 1, I'm going to get 2. If I multiply 2 by 1.5, I'm going to get 3. So automatically I have all the whole numbers. So I'm going to stop at that point. If I was not in a position to get the whole numbers, I could have continued. So I just take 1 and multiply by 2. You multiply by the same number, then 1.5 also multiply by 2. So here the answer is 2. This other side the answer is 3. So those are now the whole ratios, the whole mole ratios. So after finding that, then we just replace, because the first column here was for the iron, the second column here was for the oxygen. So we just say that Fe, which is for the iron, there are 2, and the second column, which is for oxygen, there are 3. And that's your empirical formula. You don't swap them like the case for the chemical formula when you're using valencies. In empirical formula, the answers are they already match each other. They are in their final state. You don't swap them. The answers are in their final state. We just pick what is here, you replace it where it's supposed to be, which is for the iron. You also pick the one for oxygen and you do the same. So that will be the empirical formula. So that is how we have done it. Yes, so that is how you do it, and that's how simple it is done. So that is how it is done every other time. That is how you do the empirical formula. Very simple, very easy. That is how you approach the empirical formula. That is how you approach the empirical formula. That is how you approach the empirical formula. Let's go to molecular formula. Molecular formula. Yes. So let's talk about molecular formula. Before I talk about the molecular formula, let me share with you what it means. So sometimes in chemistry, it is not necessary for you to simplify. For example, in chemistry, there's something called hydrogen peroxide. Okay, there's something called hydrogen peroxide. And how do you write hydrogen peroxide? Hydrogen peroxide is written this way: H2O2. Okay, so you normally do not divide, because if you divide both sides by 2, you're going to find 1, which we can later translate to HO. Okay, but according to the rules of chemistry, especially for the naming, there's always a body in chemistry called the IUPAC. Okay, they are responsible for naming the chemical formulas, the names of compounds and all that. So the chemical formula that they had approved for hydrogen peroxide, it was supposed to be left in this manner: H2O2. Okay, so you don't divide it. So this one are the actual number of atoms. We have not divided by anything. So those are the actual number of atoms. Then there's also sodium peroxide. Sodium peroxide. So sodium peroxide, that is how also it is written. So it means that in sodium peroxide we have 2 atoms of sodium and 2 atoms of oxygen. We also do not divide them. There's something called benzene. Benzene is written as C6 and H6. You also do not divide, because if you divide, you're going to find CH. Okay, so you don't divide. So benzene is C6 and H6. Okay, C6 and H6. So these things are example of molecular formulas. So molecular formulas, when you leave your answer with the actual number of atoms. So what do you find? You find the molecular formula. So molecular formula are basically when you leave your answer without dividing, because in the empirical formula you simplify them to the later stages, but here in the molecular formula you don't. For example, you can also have something like this: C2H2H4. So if you leave your answer that way, this one is a molecular formula, because if you wanted the empirical formula, we could divide both sides by 2 by 2. Okay, but in molecular formula you leave your answer without dividing. So that is now the molecular formula. So in exam you can be asked what is molecular formula. You can be asked what is molecular formula. I can always ask you that. In exam, I've circled it in green. So molecular formula shows the actual number of each kind of atoms present in a molecule of a compound. So it shows the actual number of atoms in a compound. It shows, okay? Yes, molecular formula. It shows the actual number of atoms in a compound. It shows the actual number of atoms in a compound. That's what molecular formula is. Okay, let's look into an example. Which example is good? Let me check. No. Let's look onto this. This example is a good one. This one is a good one. Let's do this one. Yes, a compound of carbon. So we are doing an example in molecular formula. A compound of carbon, hydrogen and oxygen contains 54.55% carbon, 9.0% hydrogen, and 36.6% oxygen. If its relative molecular mass is 88, what is its molecular formula? Then in bracket, you have been given the molar masses as usual. Carbon is 12, oxygen is 16, hydrogen is 1. So we want to solve it. So as usual, we solve it just the same way as the empirical formula. We follow that path, but at the end there's something small that we fix at the end. So as usual, you write, this is how it is solved actually. The element, you write the element, and we have 3 of them. We have the carbon, we have the hydrogen, and we have the oxygen. So carbon was the first, hydrogen was the second, oxygen was the third. Then you normally below it you write the composition, percentage composition. Write the percentage composition. Then you just copy paste them. Carbon add 54.55%, hydrogen add 9.09%, oxygen had 36.36%. So you write them. Then after that, these are the molar masses, okay, which you can also call them the RAM. So the RAM or the molar masses, but writing molar masses is much better. So use molar masses. Molar mass. So you do it in a table format. So molar mass. So molar mass for carbon is 12. Molar mass for hydrogen is 1. You take them from the bracket and you write them here. Then oxygen as a molar mass of 16. Oxygen as a molar mass of 16. Then we go to the number of moles. You must always find the moles. And remember, moles is mass in grams over molar mass. Mass in grams over molar mass. And remember, I told you in this question, the percentage composition act as the mass. The percentage composition act as the mass. So we are going to take the percentage, which is 54.55. You divide by the molar mass. So if you do so, you get 4.55. You also go to the next one. the percentage composition which act as our mass, 9.09, you divide by the corresponding molar mass, which is 1, you get 9.09. Then you go to the last one, percentage composition, which is 3.636, which act as our mass, you divide with our corresponding molar mass, which is 16, you get 2.27. Then you go to the mole ratio. So we have these three answers. We have 4.55, we have 9.09, then we have also 2.27. So how do you go about it from that point? You divide, you check all those numbers, all those moles, you check all those answers, then you divide everywhere with the smallest value, with the smallest number. So here we had 4 point something, here we had 9 point something, then here we had 2 point something. Of course 2 point something is the smallest, so 2 point something is the smallest, so you normally pick the smallest number and you divide it with everything. So now we are going to divide these moles because we want the mole ratio, so we divide by the smallest number of moles. So divide everywhere with now the answer which was here 4.55, you divide by the smallest, and the answer which was 2.27. The answer which was here, you rewrite it again here, 9.09, you divide by 2.27, then 2.27, you divide by the very same 2.27. So automatically here you'll get 1. If you divide the same thing, of course there is 1. Then you try and divide this one, you're going to get 4.004. If you divide this one, you get 2.004. So I told you that 2.0 you can round off. Anything when you have 2.0 you can round off because we want the whole numbers. We have the whole numbers. So 2.0 can be 2, 4.0 can be 4, and 1 is already 1. Okay. Then after that, then there's something that we need to do. We don't just stop at that point. So we don't just stop at that point. So up to that point we can find the empirical formula. Up to that point we can find the empirical formula where carbon, which is C, so the empirical formula, carbon which is C has the 2. Carbon which is C has the 2. Hydrogen which is H has 4. And oxygen as 1, where 1 you can just ignore. So we are still not yet done. So there's always a formula. After that, there's always a formula that says that empirical mass N into empirical mass, N into empirical mass is equals to molecular mass. Is equals to molecular mass. N into empirical mass is equals to molecular mass. If you can multiply it by N into empirical mass is equals to molecular mass. Okay, what do I mean by this? For example, even the molecular formula. Let's talk about the benzene. You see, we have the benzene. Benzene is C6H6. So, and what would be our empirical formula? Because empirical formula, you're going to divide everywhere by 6. Divide by 6, you get 1, 1. So empirical formula would be CH, because empirical formula you divide. So how can you get back to 6? How can you get back to C6 or H6? By multiplying this thing by 6. So 6 is our N. So empirical formula is always going to be less. So you need to multiply it by a certain factor to get the molecular formula. So if I multiply here by 6, 6 multiplied by this C, I get my C6. 6 multiplied by this H, I get H6. So that is where the N comes into play. So that is now the role of N, so that we can get the factor. We can get the number that we need to multiply the empirical formula with to get the molecular formula. So it works in two cases. So you can say N multiplied by empirical mass is equals to molecular mass. You can as well say N into empirical formula is equals to molecular formula. So that is how you go about it. So that is the relationship that I've just written here. So we just substitute it out. Okay. So this is our empirical formula, or so the empirical formula. So this empirical formula will give us the empirical mass. So as you can see here, C2, then you now proceed after writing this, which is in red, then you now proceed. This is our empirical formula. So empirical formula is C2 because we have taken it from using these values and we have substituted here. So we have C2H2O2. So we are going to say that C2H4 and O then multiplied by N will give us the molecular mass. This one was in the equation. It was here. Let me show you. It was here in the equation. As you can see, we were given here molecular mass. It was there in the equation. If its relative molecular mass is 88, it was there in the equation. So that is where I've got it from. So we equate it. So, and remember, we have the molecular masses. Remember, we have the molar masses. And remember, we have the molar masses. So you now substitute. Carbon is always 12, but there are two of them. Carbon is always 12, but there are two of them. So you take 12, you multiply by 2 plus hydrogen. We have 4 atoms of hydrogen, and the molar mass for hydrogen is 1. They are in the bracket here. Those values are in these ones. These are the molar masses. This is where we get them. So they are here. Carbon has a molar mass of 12. Oxygen has a molar mass of 16. Hydrogen has a molar mass of 1. Okay, so that is where I'm getting them from. Then we now proceed and substitute. Hydrogen has 4 atoms, so 4 times 1 plus oxygen is only 1, so 16 times 1. So you add all of these, that is 24 plus 4 plus 16. You get a total of 44 times n, you get 44n. So 44n is equivalent to 88, but you want this n. So divide both sides by 44, divide both sides by 44, n is 2. Because if you divide both sides by 44, 88 divided by 44 is 2. So after getting 2, 2 is our factor. Okay, 2 is our factor. So 2 is our factor. So if 2 is our factor, so now you take your, because you take your empirical formula, the initial empirical formula, which was C2, it was H4, and it was just O. Then we are now going to open it with 2. We are now multiplying it with 2 because 2 is our factor. Then you go ahead and take 2, multiply by 2. You are now going to get C4. Then you go to this 2, multiply by 4, you get H8. And now this one had nothing, so it takes the 2. So this one becomes our molecular formula. So that one becomes our molecular formula. So that is how we have done it. So that is the entire question. And that is how it's supposed to be done. That is how it's supposed to be done. So it's simple, it is easy. I believe you are in a position to, you can attempt this one, the very first example. You can attempt this one. Let me run this. Yes, so your assignment, which you can try and work it out, the answer is already here. No, yes, you can check on this example to see if you are in a position to do it. Okay, this is another example after finishing the other one. So you can write this question, and you work it out. So the answer is here at the bottom here. Okay, so if in case you are not able to do it, then you'll be able to refer to the answer is already here. So this is your assignment that you can try. It is a small exercise to try and see if you are good at it. So the question is here, and the answer, I've also presented the answer. So you'll write the question, you'll try to do it, then you'll compare your answer. In case if you're not able to get the answer that is here, then you'll try and follow on this, or you can as well contact me later on. So that will be the end of our first class in moles. This is our part 1. I'll upload more videos on moles till the end. Thank you so much for listening to this. See you in the next session. So we'll be starting on, so the next thing we'll be doing in part 2. In part 2, we'll start on molar solutions. So in part 2, we'll start on molar solutions. So today we have covered, let me show the table of contents. So what have we covered so far in moles? Sorry for this, but let me share the table of contents. So far we have talked about the relative mass and the Avogadro's constant, and we have covered empirical and molecular formula. So in our first part, these are the two things that we have covered. So in the next part, we'll be focusing on molar solutions. Thank you so much. Bye bye.